All right, how's everybody doing? So as usual, remember to do the seating survey. Upcoming deadlines, this week's content video quizzes are due today. There is an error in one of them. I think most of you have gotten through that already. The instructions for how to deal with the error are under the link that takes you to the video. So just take a look at that and it should help you out. Tomorrow at 5, the first midterm exam becomes available. This week's homework is due Friday at 5, and the midterm exam number 2 is due Sunday at 5. The details on the exam are on Piazza, and in case you haven't noticed it yet, I'm going to switch to looking at Blackboard for just a moment. So on Blackboard, there is a link here for resources. If you go to the resources page, several things on here. This top one is a tool I have put together for cataloging the intermolecular forces between either similar molecules, the same molecules, or different molecules, so that you can use that information to identify issues related to boiling points, vapor pressures, things like that, or solubility if you're looking at the at two different types of molecules. I know that some people were having trouble identifying when something is ionic and when it's not, and so that's why I have a link here to the common ions and their charges. I have a video walkthrough of small group activity number 2, and then I have here the system information, background information for the first midterm exam. So the midterm is organized around 4 different systems, and I am providing to you in this document some background information on those systems. So the first one here is seawater and some background information. The second one is looking at ionic crystal structures, and I give you some sizes of anions and cations and some information about how ionic crystals work. I have here some information for system 3, which is looking at the surface level atmosphere of Mars and Venus. So we have atmospheric composition and the properties such as the temperature and the pressure of the atmospheres of Mars and Venus. And the fourth system is looking at a series of what are known as hydrofluorocarbons. So we've got the list of the hydrofluorocarbons, their boiling points, and some comments about them, as well as links to places where you can see 3D structures of them if you wish. So for example, if we want to look at this molecule, we can copy that. We can go to this link, put that structure into the search, and scroll down, and you can see here a 3D structure of that particular molecule. Okay? These kinds of things will help with evaluating things like polarity, dipole moment, that sort of thing, and making sure you have a 3D visualization of what the molecule is as you're trying to figure out things like intermolecular forces surrounding them. So the reason that I am providing this resource to you early is so that you have opportunities during the class periods today and tomorrow before the exam is actually released to you, and during my office hours and such, to familiarize yourself with the systems that the exam questions are going to be asking questions about, so that I can help clear up any confusions that might be present about them. So the idea is that these systems are a way for me to organize the questions I'm asking. I'm going to be asking questions about the the content we've been discussing. It's not like new stuff here. But I don't want each question to be, okay, I now have to learn something new to answer an application question about a new system. I want it to be a limited number. So you've only got these 4 systems that, that the questions are going to be applied to. So that's the general idea of this. So as you, and I will bet you that you can look at the, look at this document and make some predictions pretty easily about what types of questions are going to fit into which of these various systems. So seawater, for example, I have here a list of ion concentrations. I have a list of solubilities of various compounds, sodium chloride, sodium sulfate, and so on. So what kinds of questions do you think might fall into this particular system? Anybody give me an example? Where have you used ion concentrations in this class? Have we used ion concentrations in this class? Yeah, so what kind of area? What kind of questions use ion concentrations? The chat says osmotic pressure. Yeah, colligative properties, absolutely. That would be a perfect kind of question to ask about this kind of material. Notice that some of these concentrations are really small. You know, 0.001 parts per thousand by mass. Now, is parts per thousand by mass a unit that we use have used very regularly so far? No. So maybe converting these concentrations to something we more regularly use in chemistry might be a step along the way to answering some of these questions. Right? So just by looking at what information you're given in these cases, you can predict pretty readily, just by looking at the topics that we've covered, the kinds of things you might end up needing to do as part of the exam. So this document now being available gives you a day and a half, 2-day head start on trying to think about those questions before the exam even becomes available. And you can still ask me clarifying questions once the exam becomes available, you know, because you don't have to take it until Sunday if you don't want to, for example. So there'll still be plenty of time to ask questions of that type. And I'm going to be very diligently keeping up with Piazza during the exam time so that if any questions come up, I can address them. So my request on that is that if you have a general type of question about content that there's some way you can ask it without asking specifically the question that is on the exam, make it a public post, even if you want to do it anonymously, because other people may have that same question. So if the question that is on the exam has to do with, say, magnesium sulfate, then maybe you can say, I know the exam question talks about magnesium sulfate, but can you explain this particular aspect related to potassium bromide instead? And then that's the kind of thing that I could absolutely provide some guidance on in a Piazza kind of question. Okay. All right. So any questions on logistics before we get into today's content discussions? Okay. Let me turn that off, switch back to the document camera. Okay. So the muddiest points that are currently listed on Piazza are all having to do with the kinetics material. So that is where we will start. And then once, there aren't very many, so once we get through them, we will open up the floor to any kinds of questions we want to look at. So there are quite a few, I mean, the top three here are all kind of related. Just, you know, we have these different kinds of reactions, first order, second order, zeroth order. We have rate laws. Trying to just get the brain around what does all this mean? Why do we care? What does it mean for something to be a first order or second order reaction? These sorts of things. So I'm going to start on that by addressing this part, the importance of it, so that you have sort of a context for why we're even talking about this stuff in the first place. And I'm going to go through three brief examples that are going to illustrate this idea. So the first example is looking at questions of ozone in the upper atmosphere. Ozone's particularly important because it blocks a particular type of ultraviolet light, and that particular type of ultraviolet light is dangerous to biology. It can cause cellular damage. And so what we find is that to large measure, the amount of ozone that is in the atmosphere, ozone here is the O3 molecule that we have in those two reactions. That amount of ozone is determined in part by how much NO2 and how much NO there is. So if we look at these first two reactions, NO2 gets hit by light. It breaks into an NO molecule in the gas phase, and that's an asterisk up from the oxygen. So there's an oxygen atom that is floating around free that is in what's called an excited state. It has some extra energy in its electrons, so don't worry too much about that. But then that excited oxygen atom can run into another oxygen molecule along with some other gas particle. M here just references some other gas particle that it can run into at the same time. And then those two can combine to form ozone. Okay. But notice here that the first reaction here makes NO as well, and NO can react with ozone to get rid of the ozone. So we've talked a little bit already about this concept of dynamic equilibrium, where you have a reaction going one direction, and then you have the sort of a reverse reaction going the other direction, and you have a constant amount of each of the reactants and the products, but that amount depends on how fast the forward reaction is going compared to how fast the reverse reaction is going. So we have our forward reactions 1 and 2 here that are going to progress at some rate, at some speed. And then we have the reverse reaction, reaction 3, that's going to progress at some speed. And the balance between those is going to determine whether we've got any ozone in the atmosphere or not. Okay, so this is the kind of question that the elements of kinetics can help us understand. Because if we can demonstrate what the rate law is, then we know that, that the higher the concentration of O2 we have, the faster this reaction is going to be. And if we know what the rate coefficients are, then we can numerically determine just how fast the reactions are and figure out what the balance is between going forward and going back. So that's the first example. Second example I'm going to look at is a related kind of concept, also a dynamic equilibrium, but this is an industrially important reaction called the water-gas shift reaction. And it is a reaction that is used to commercially produce hydrogen gas. And hydrogen gas is used in industry for a whole host of things, making various kinds of pharmaceuticals, in fact, because you use the hydrogen gas to take a double bond and make it a single bond, and you're trying to react things away. Well, understanding how fast this reaction happens, both the forward and the reverse direction, and then something we're going to get to next week, how changing the temperature of the reaction can change the speed of the reaction. And then adjusting the partial pressures of the reactants, adjusting the partial pressures of the products can help you take this reaction and make it economically viable. Because if there's a temperature range where you optimize the generation of H2, you don't want to go higher in temperature than that. You need to figure out how to do that. And that comes down to how fast is the forward reaction versus how fast is the reverse reaction. That's a second example. The third example I'm going to look at is really looking at chemical engineering in a sense. So this is a chemical reactor. And the idea of this chemical reactor is that we are bringing in from one side waste that has organic molecules in it. And we want to break down those those organic molecules so that the waste has now been treated and is not going to be a contaminant out in the environment. So the way this works is that we bring the waste in here, we bring in oxygen, and we bring in supercritical water. So we talked about the supercritical fluid region of the phase diagram. This is a reactor that is happening where the solvent is supercritical water. And what happens here is that the oxygen will react with the organic molecules that are coming in and oxidize them in order to destroy them. It's basically like a controlled burning kind of thing that's going on. And what happens is that the reaction starts here, but it's flowing. And so there's a certain amount of time between the reactants coming in and when the reactants leave the reaction region and then start getting separated into products that either vaporize and go up or products that sink and go down. Because this region here is cooler and at lower pressure than this region here. So understanding the rate of the reaction, how fast it goes, tells you how long this tube from here to here needs to be in order to allow the reaction to run to completion and everything to have been reacted away. So that's another example of where we use this kind of information of kinetics, of reaction rates. Now, actually solving this kind of problem involves a lot more than just the reaction rate law itself, because we need to understand the flow rates, and there are a lot of chemical engineering concepts that go into it. But a very important part of solving that problem is reaction rates. So I hope that that explains a little bit of some examples of where rate laws can become kind of important. Any questions on that before I get into some of the more detailed aspects of it? Okay, so let's now talk about the order of the reaction order. Okay, so I want to look at that in a couple of different ways. The first is in the differential rate laws. Okay, so a rate, which remember the rate is a derivative. It is the change in a concentration with respect to time. Our rate is very often of the form a rate coefficient times a reactant to some power. We'll call that power A. In this, usually A will be an integer. It can sometimes be a fraction. 1/2 is the most common fraction you will see. It can sometimes be negative, but most often it will be either 0, 1, or 2. And that is where the reaction order comes from. A equals 0 is a 0th order reaction. A equals 1 is a first order reaction. And A equals 2 is a second order reaction. Those are by far the most common cases for a rate law that only involves a single component. Okay. So that's where this reaction order terminology comes from. And what we have when we do this is a something called a differential equation. So this is going to equal d concentration A dt, the derivative. And in the integrated rate laws content video, I went through solving these differential equations. Not because you need to solve them. I'm not going to ask you to do calculus in this class. I was taking you through it so that you can see what the solution is, so that these different equations, once it's been solved, will make a little bit of sense to you, rather than, oh, those equations are magically coming out of nowhere. So that's all I was looking at in going through those. And the results of that solution are that for a 0th order equation, we have the concentration of our species equals our initial concentration of the species minus kT. For the first order equation, we have the concentration of the species equals the initial concentration of the species times e to the minus kT. And then for the second equation, or second order case, we have a slightly more complicated looking expression that looks like this. Okay. So you already know I do not expect you to memorize equations. So on the exams, it is perfectly fine to be looking these up so that you don't have to remember that this is the second order equation, this is the first order equation. But the determining which of these to use comes, which is a common question I've been getting, comes down to which order is it. Okay, so in this, when you look at the plots of these, of concentration versus time, the 0th order basically is a straight line going down. The first order is a curve that looks like this. And the second order looks like kind of like the first order, but it's faster at short times and it's slower at long times. Okay, so in these, the general idea, and the reason it's important to know which order it is that in this case, in the 0th order case, you're going to have a constant amount of the reaction happening at every point in time. Okay, you can't really speed up or slow down the reaction. It's happening at a constant speed. For the first order reaction, the more reactant you have, the faster it goes. For the second order reaction, that same thing is true, but even more so. The faster the more reactant you have, the reaction goes like gangbusters. Okay. Now, how do you, if you have the differential rate law, then determining which reaction type you have just means looking at the exponent. How do you find that experimentally? How do you figure it out? There are 2 different ways to do that experimentally. One of them is to use the method of initial rates. which I went over in the very first of the kinetics videos. The simpler way is to plot three things. If you plot concentration of A versus time and get a straight line, it is 0th order. If you plot the natural log of concentration versus time and you get a straight line, it is 1st order. And if you plot 1 over the concentration versus time and you get a straight line, it is 2nd order. And we get that from these equations and these equations and manipulating them into what's called the linearized form, which I also did in the integrated rate law content video. So, the goal of kinetics is to find the rate law, because once we have the rate law, we are able to predict a future concentration given initial conditions that we're starting with. That's the goal. Achieving that goal means finding the reaction orders and finding the rate coefficient. Okay. I've shown you here how to find the reaction order for a case where there is only a single species. Finding the rate coefficient from these is quite simple because the slope in this case is negative k. The slope in this case is negative k. And the slope in this case is positive k. Okay. So, that is why you need to know the slopes of different laws and if it's a straight line or not, because it tells you the reaction order. Okay. The order of reaction equations, this is where they come from. These are the categories, and these are the results of solving them. And the meaning is simply just what is the exponent in the differential rate law. That's all it means. We'll come to this last question about 0th orders in a moment. Are there any clarifying questions you guys have about the ideas of rate laws and the special cases of 0th, 1st, and 2nd order? Yes?
If you don't have a graph of the thing, how would you find K?
If you don't have a graph, how would you find K? Okay, so if you don't have the graph, then you might need to use a method like the method of initial rates to do it. So you would need to have some piece of information about the rate in order to find K, and so that would be the main thing. If you are told that it is 1st order, for example, and you are given 2 points, a concentration at one time and a concentration at another time, then you could make yourself a graph and just determine the slope from that. Okay, so I haven't looked very closely at what the Newton questions are on this kind of material, but I could imagine that they might do something like that, where they would say, here's a concentration at this time, here's a concentration at this time, it's 1st order, find K. And so you would make yourself a graph, even if it's just 2 points, and by doing natural log versus time, and find the slope. Any other clarifying questions? Kinetics in general. Okay, let us talk about the last question from the muddiest points list. Zero order reactions, always going to equal 1 at all times. How is it possible to have a reaction if the concentration is 0? Okay, so the 0th order reaction is kind of the weird one of the case, because if we look at the rate, K A to the 0th, anything to the 0th is 1. So this just equals K. And so that says that our change in concentration with respect to time is going to be a constant value at all times, right? And then if we plot that with a constant slope, you get this. But the math says you can keep going, right? And does a negative concentration make any physical sense at all? No, not at all. So what is going on here is that the 0th order reaction is valid within a given concentration range. And so it'll be 0th order up to some point, and then at that point, it stops being 0th order and then starts being something else that may look maybe 1st order or something like that. Okay. This will make a little bit more sense next week when we talk about reaction mechanisms, because a 0th order reaction is always a multi-step process. So I showed that example earlier of this one, where the formation of ozone proceeded by 2 steps. What can happen is that that pair of steps will usually have one of the steps being what's called rate determining. It's the slowest one. So if this first step is really slow, and this happens really fast, then the overall rate of ozone formation is going to be determined just by the first reaction. Similarly, if the second reaction is really slow and the first one is really fast, then the overall formation of ozone is going to be determined by the second reaction. But what can happen over the course of a reaction proceeding is that you can sometimes switch which one of them is rate determining. So if this step is the fast one, but then you run out of NO2, then that one's going to end up becoming slow because there isn't much NO2 to react. Okay, so what's happening here is that we have 0th order for a while, and then the mechanism changes because you're running out of one of your reactants, and so which step in the multi-step mechanism is rate determining switches, and so it goes to another form. I am not going to be holding you responsible for that, certainly not this week. I haven't looked fully at how deeply we're going to go into mechanisms next week. But the instinct behind this question about, 0th order sure looks like it should go to 0 concentration. What happens at that point? That's an excellent instinct to say something weird is going on there. And here's the explanation for it, even though I'm not holding you responsible for that. Yes? Say that again? So the midterm that is getting released tomorrow does not have kinetics on it. This week's material is going to be on the second midterm, not on this midterm. All right, any clarifications on the 0th order stuff? Yes? 5 o'clock. Yeah. Okay, I will open up the floor and the chat to any questions anybody has. Yes?
When we try to
calculate for the exponents to find the reaction order, you end up with a decimal. How would you round?
Excellent. Okay, gotcha. So is this like the method of initial rates? Is that how?
So I have K, A3M, B3N over, and then you have the concentrations at each of those steps as well as the rates.
Okay, right. So the question is, how do you end up rounding when you are using a method, if you're trying to find a reaction order and you're finding something that seems to be a decimal? So this is a kind of issue that might arise when using the method of initial rates. Would people like me to go through an example of the method of initial rates? Would that be useful? And then I can do that kind of thing. Okay, so the idea of the method of initial rates is that we have some kind of reaction where the rate is going to be K times a concentration of A to some power, concentration of B to some power, and concentration of C to some power. And we are going to start the reaction. So we're going to have an initial concentration of A, an initial concentration of B, an initial concentration of C, and a measured initial rate. So what I mean by a measured initial rate is that if we plot concentration of A as a function of time, then we take the slope right at that very first point, okay? So the tangent right at that point. So if we start with concentration of 0.1, 0.1, 0.1, and just for simplicity, let's say that we have a rate of 1 in some units. Now we double the amount of A we have, 0.2, but leave everything else the same, okay? And let's say that that ends up doubling the rate. What's going on here is that we can take this expression here and ratio it. So we have R0, we'll call this A, this B. R0A over R0, let's do R0B over R0A. And that's going to equal this for the first case over this for the second case over this for the first case. But a bunch of the things are going to cancel. The K is the same, the B concentrations are the same, so the only thing we have is concentration of A to the A in experiment A. I shouldn't be using A in both these cases, should I? And that should be a B. A to the A, concentration B down here. Geez, I keep A. Screw it. We're going to make this 1 and 2. 2, 1, 2, 1. Okay, is that better? All right. But we have numbers for these things. So we have here 0.2 over 0.1. In this case, we can take the A power outside, so we have 2 over 1 to the power A, right? In this case, the way I did it, it's pretty clear that this fraction is 2, this is 2 to the A, and so A has to be exactly 1. Except if you're dealing with real experiments, it's not going to be that neat and clean probably. You're going to have some level of measurement error in your measurements. And so maybe this ends up being 1.03 and this becomes 2.01, okay? And so when you do that, you're going to get 2 equals, that's going to be, I don't know what that's going to be, but it's going to be 1.9 something to the A. And so, off screen, sorry. 1.9 something to the A. And so determining what A is, it's not going to come out to be exactly 1. So the question then is, how do you round it? How do you determine what the, how close to round it is? Hopefully the examples you'll be working with will have cases where it's really close to an integer or it's really close to a half integer. There are not many cases where reactions have orders that are non-integers or non-half integers. So if you've got something that's like 0.48, then you would absolutely say that's 1/2. Okay. If you end up with something that's like 0.33, yeah, that then either it's a really weird reaction or there's something wrong with the calculations that got to that point. Is that, yes?
Should we round to the nearest integer? Or so say you have like 1.25 or 1.26, would you round?
Well, 1.26 is halfway between 1 and 1.5. So I would have trouble rounding that one myself. If it's like 1.1, I would absolutely round down to 1. But once you start getting that in that sort of 2.5 kind of range, I would say that that something weird is going on. Okay, any other questions on numerical aspects of kinetics at this point? Okay, looks like there is there are a couple of questions from the chat. One of them is, do the orders essentially describe the behavior of a substance as it reacts? Kind of. It certainly describes the behavior of the concentrations with respect to time as it reacts. We will find next week that for certain types of reactions, there is a relationship between the reaction stoichiometry and the rate law. So I briefly mentioned the idea of a multi-step reaction. If you know that a particular reaction step is in fact it doesn't break down into sub-steps. If you know that this is an elementary reaction is what it's called, where this reaction happens by a molecule of A running into a molecule of B, and that collision then produces the products, then you can write down what the rate law is for that step. In this case, it would be the rate law is some rate coefficient times the concentration of A times the concentration of B, because the more A you have, the more collisions you're going to get. The more B you have, the more collisions you're going to get. If you know that a single step is A plus 2B, so you have to have a three-way collision between one A molecule and two B molecules, and you know that that is a single step, then you can write down the rate law for that step is AB squared. Okay. So for elementary reactions, there is a connection between the reaction stoichiometry and the rate law. The problem is that proving that a step, that a particular reaction is in fact happening by a single step is non-trivial. And so there are plenty of cases where there's a reaction that happens, where you have a stoichiometry and the rate law doesn't directly come from the stoichiometry, demonstrating that it is a multi-step reaction. Okay. So, I have a question from the chat that is not about the kinetics. So, asking to go over another example of how to determine the largest atom that could fit inside a unit cell. Okay, I'm happy to do that. So, let us talk about. Okay, so the exam background information tells you that you're working with a face-centered cubic structure for the anions. So I don't want my example here to be that face-centered cubic example. So I am happy to do either the body-centered cubic or the simple cubic. Does anybody have a preference? No? Okay, so the chat is requesting body-centered cubic as well, so we can do that. All right, so let us draw ourselves our body-centered cubic lattice, or unit cell, excuse me. Okay. So we have our atoms at the corners, which are not in contact with each other because they've been pushed apart by the atom that is dead center. That atom that is dead center, I didn't scale this very well. I didn't scale it well at all, is in direct contact here and here across the body diagonal. Drawing this might actually be easier. I mean, finding a picture might actually be easier. Let's do this. We have that. Let us go to, let me close this. No, I don't want the. Nope, there. Okay, so. What did I just do? I don't know what I just did. Okay, here we go. Okay, so what we have here is the body-centered cubic structure. We have contact between the central atom and the opposite and all of the corners. And so the body diagonal from this corner to this corner corresponds to one radius, two radii going through the central atom, and one more radius here for a total of 4. Yes. Thank you. All right, so trying again. So this is the body-centered cubic. We have the red atom that is in the center. It is in contact with each of the 8 corners of the cube. And so a line that is entirely constructed of radii goes from this atom to its edge, fully across the central atom for 2 radii, and 1 more radii to get to this corner, so that the body diagonal is 4r. Okay. Now, the next thing we need to determine is where are the interstices that we have to worry about. Okay. And it looks to me, looking at this, as though the largest space that we have would be dead center in a face. Can you see that? Dead center in the face? All right. So if we look at that from, I'm going to switch back to my drawing, make sure both the class and the chat can see that. I'm just going to draw the front face. Okay. We've got this here, and the largest sphere that will fit in here is going to be like that. Does that make sense? So what we need to do then is find out what the face diagonal is. So let's go back to the body-centered cubic portion for a moment and remind ourselves of what the body diagonal is relative to the edge length. Okay, so we know that the body diagonal, so I'll say diagonal body, is going to equal 4r, a radius, 4 atomic radii. And since we're talking about putting something in the interstices, these are going to be the anions, and this thing here would be the cation, right? So I'm going to call this 4r sub a for the anion radius, okay? Now, let's use some Pythagorean theorem, okay? So this is a right angle, and that's the face diagonal that we have there, right? So and this is an edge, and this is a face diagonal. We'll call that d sub f. So Pythagorean theorem says d sub f squared plus e squared equals our body diagonal squared. Everybody with me on that? Yeah, okay. Now, but we know what the body diagonal squared is, that's 4RA. So this then becomes 16RA squared. Right? Now, we also have the Pythagorean theorem that we can use to connect the edge sides to the face diagonal. So e squared plus e squared equals face diagonal squared. I labeled this wrong. That should be a d sub b. Okay. So does everybody see this one? Okay. Continuing on, we can simplify this one to 2e squared equals df squared. Take this, we now can plug the df squared into here, right? So plugging this in for that, we have 2e squared plus e squared equals 16RA squared, right? We can combine over here. 3e squared equals 16RA squared. And we can find that, let's divide 3 by the 16. No, wait, which do we want to solve for? Let's solve for e. So e squared equals 16 over 3RA squared. And then e equals 4 over the square root of 3RA. Now that we have an expression for e, we can find df, which is the thing that we needed, right? So 2e squared equals df squared. So e squared we already have here. So 2 times 16 over 3 RA squared equals df squared, right? So take the square root of this. Our df is going to be, let's see, 2/3 square root times square root of 16 is 4, Ra. Now, what did that get us? Let's actually plug this into a calculator and see what that is. So 2 divided by 3, square root that times 4 tells us that the face diagonal is 3.27 Ra. Now, if we look at our picture of the face diagonal, this is an Ra, and this is an Ra. So the diameter of the cation, is going to equal the face diagonal, 3.27 Ra, minus 2 Ra, because we have 2 Ras, equals 1.27 Ra. And so if that is the diameter, the radius is just half of that. So 1.27 divided by 2 . So I subtracted 2 and then divided by 2. So the radius of the cation that we have there is going to be 0.63 times Ra. So the cation that would fit perfectly into that spot would have a radius that is 63% of the radius of the anion. So does the procedure there make some sense? All it is some geometry. And fortunately, we didn't even have to go to trig or anything to do that. It was just the Pythagorean theorem. Okay. So one of the pieces of information that I included in the systems document was talking about what happens if you are dealing with cations and anions, and do you need to be smaller than this size or larger than this size? So if it's smaller than this size, then it'll fit into the space, no problem. But think about the anions. The anions across the body diagonal are going to be in direct contact with each other, right? They're charged the same, so they repel. So that's not good. So actually, this is the minimum size for the cation. You want something that is larger than this so that it will force the anion lattice to expand so that the anions will not be in direct contact with each other. Does that make some sense? So what you could then do, if you're given an anion, is look at the radii of cations and figure out, okay, which of them are larger than this cutoff. Those can go into this structure. Which of them are not larger, they won't be in this structure. Does that make some sense? Okay. Another thing you can do with this kind of problem is to ask yourself, what would the packing density be? Because now we've got two different kinds of spheres that are taking up the space, right? So it comes down to, well, we have an edge size, right? So you cube the edge size to get the size of the cube, and that gives you the unit cell. And the thing that's inside of it are going to be the anions. So 4/3 pi radius of the anion cubed, plus the same thing for the cations, 4/3 pi radius of the cation cubed. And each of these are now going to be multiplied by how many anions are in that unit cell and how many cations are in that unit cell. And that then will give you the packing density for the resulting ionic compound. So with that in mind, let's take a quick look here. I'm going to switch back. If we look at this body-centered cubic structure, and we said that the holes we are looking at are in the center of the faces, how many holes do we have? There are 6 faces, all right? So they're going to be 6, but each one is only half inside this unit cell. So you're going to have 3 of those atoms in this case. Now, an interesting thing about that is how many of the anions are there in this unit cell? There's 1 in the center, but then there's an 8th times an 8 for each of the corners, right? The gray and the red here are the anions. The cations are the ones we're imagining putting at the center of each face. So this unit cell that we've just described has a 2 anion to 3 cation ratio. And so that's not going to work for something like sodium chloride or something, right? You would need something where the ratio of the anions to cations is the correct 2 to 3 ratio. Okay. Yes?
Can you also go over like the coordination?
Coordination number, sure. So coordination number is very simply how many nearest neighbors are there. So in this case that we're looking at, if we look at the central red atom, how many atoms is that central red atom in direct contact with? 8. So the coordination number is 8. Now, if we're talking about an ionic compound, then the nearest neighbors are going to be the oppositely charged species. Okay. So if we had this body-centered cubic structure, and we do in fact have the correct 2 to 3 ratio of the anions to cations, and every face has a single cation in it, what would be the coordination number of the cation? So it's going to, so if we imagine the front face here that I'm using, putting the mouse over, we're going to have 1, 2, 3, 4 that's in direct contact with, 5, the central one, and the corresponding red one in the other, on the other side. So we would have a coordination number of 6 for that. Yes?
Is it not also in contact with the 4 corners on the other?
No, because remember that we said that the cation has to be larger than the space that's available in order to push the anions away from each other. Well, you have the same issue the other way around, so that the cations can't be in contact with each other either. Okay. Okay, so did that help? Okay. All right. We have about 6 or 7 minutes left. What else can we chat about? Let's see. Say that again, please. Sounded like you said you want something larger than the space. So we figure out the space that it would fit, and then we go bigger than that radius. Yes. So the idea is that if we look at the size of the hole, the interstices, assuming that the anions are in contact with each other, what we put into that hole has to be bigger than the available space so that the anions are forced away from each other and as a result are not in direct contact of negative ion with negative ion. That repulsion is just bad from an energy perspective. So you figure out the space that's available, and you go for a counter ion, meaning the ion of the opposite charge that is larger than the available space, so that the counter ions can be in direct contact, but like charged ions cannot. And then follow-up question, wouldn't that push out the anion, leaving less in the unit cell? It will push out the anions, but the unit cell size has expanded. So the unit cell size is defined by the distance between corner atoms. And if the corner atoms get further apart, you now have a larger unit cell. Does that make sense? Okay, cool. What else? All right, you guys want to call it for today? All right, thank you very much. Please take a look at that systems document and use my office hours, use Piazza, use me as a resource. I'm here to be a resource. Okay, so quick clarifying question from the chat. So a coordination number of an ionic unit cell will only include the opposite species. That's correct. The idea is that you only count the coordination number for the species, for the atoms or ions or molecules that the particular one you're looking at is directly in contact with. And because the anion structure has expanded, then you only have contact of one ion with oppositely charged ions. Okay. All right, thank you. Thank you.